Hi. Welcome to FabFest 4, brought to you by DTI, DOST, and AMSEN. Hope you can hear me. All right. So I really enjoyed the talk this morning by Matthew Fiedler, 3D printing using plastic waste. I mean, I love events like these where like makers can just compare notes and they can share what they've been doing. Today, we're doing another session, ceramics additive manufacturing, a mature technology adapted for mass production. And to introduce today's speaker, Ms. Maria Angela Lopez will introduce Maxwell.
Good afternoon. Hello again. I am Angela from the DOST AMSEN. The webinar for this afternoon will be from the 3D Ceram Cinto. 3D printing is one of the most disruptive technologies of the fourth industrial revolution. The study of technical ceramics takes advantage of this new technology by having more design options which were otherwise not possible nor practical using traditional processes. To make this technology more accessible, 3D Ceram Cinto developed a wide range of ceramic 3D printers and technical materials that can be utilized in an automatic system to increase productivity, flexibility, and efficiency. Our speaker for this afternoon graduated from the National School of Industrial Ceramics in France. He currently works in 3D Ceram Cinto as a ceramic engineer since 2013. With more than 7 years of experience on 3D printing ceramics, he led projects for various applications in biomed, foundry, aerospace, and other industrial applications. Please welcome our speaker for this afternoon, Engineer Maxence Bourgeois.
Hello everyone. Can you hear me? Is the sound is okay?
Yes, we can hear you.
Perfect. Thank you, Angela, for this very kind introduction.
You're welcome.
So I'm very glad to have you all of there on the conference. I will try to share my screen in order to show you some slides. Can you see my screen? Virtually despite the current sanitary situation. So as you told, my name is Maxence Bourgeois. I'm working for 3D Ceram Cinto as a sales manager for APAC area. And today I will speak with you about ceramics additive manufacturing, a mature technology adapted to the mass production. First, I will quickly introduce my company and our process in order to set the context, and then I will detail the subject of my topic. So a few words about 3D Ceram Cinto. It is a French company based in Limoges. Limoges, to give you an idea, it is a quite small city in the center of France, 3 hours on the south to Paris. And our company was created in 2001 by Richard Gagnon and Christophe Chaput, who are the two CEOs. Today, we are a team of 30 persons. And as you can see on the slide, we are currently building a new facility still in Limoges. We will be finished in January 2021, so in a few months. And since end of 2017, so since 3 years, Cinto Kogyo, a Japanese company, is our main shareholder. So we mostly work with a network of distributors and also some subsidiaries of 3D Ceram Cinto. As I told you, our shareholder, Cinto, is based in Nagoya, Japan. We have also a joint venture in China since 4 years. Also a subsidiary in USA since 2 years in Connecticut. And we have more than 30 partners all around the world. And since few months, we are more than happy to work with a Philippine partner. So we are working with the company OmniFab, based in Manila. You can find on the slide their contact details, and clearly do not hesitate to contact them if you have any question or project about 3D printing in Philippines. They can support you for any project about 3D printing for industry, medical, academy, and military projects. So let's come back to the topic of the day. So I think one of the first questions is, what is technical ceramics? People knows well plastic, knows well metal, but not yet technical ceramic. So we try to answer to this first question. You know, among the most innovative materials, advanced ceramics are playing an increasing important role because technical ceramics provide reliable solutions when metal and polymer have reached their limits. Today, the technical ceramics have become indispensable to the state-of-the-art industries, thanks to their unique properties. So the properties could be mechanical, electrical, thermal, optical, chemical, aesthetic, and so on and so forth. And due to these properties and their qualities, they are now one of the highest performing materials, allowing a wide range of applications in various business sectors. This is why high performance and innovations enable today advanced ceramic to address the most complex industrial challenge, as I will explain you on the next slide. You know, you have to keep in mind that there are a lot of processes to shape technical ceramics, but all the processes use the same method. We start with a powder, a raw material, then we have to shape the powder, and then to do a firing to obtain final properties. And you know, there are many technologies to shape ceramic, such as injection, milling, casting, extrusion, and so on. There are clearly a lot of process, but all the process needs tools and molds, and not 3D printing. And it is a big advantage of technical ceramic additive manufacturing compared to all the other processes. With 3D printing, as you know, you do not need any tools or any molds in order to shape ceramic, but also metal or plastic. You have to keep in mind that the activity and the know-how of 3D Ceram Sinto is to provide solutions for the 3D printing of technical ceramics. At 3D Ceram, we are only focused on technical ceramic parts. As Angela told you, I am a ceramic engineer. Our two CEOs are also ceramic engineers. So at 3D Ceram, we are a team of ceramic engineers, and we are only focused since 20 years on the printing of technical ceramics. So this is why we print ceramic parts on demand since 2001, thanks to a SLA process, stereolithography process, that we developed internally. And since 5 years, so it was in 2015, we decided to provide entire printing line to our customers. So printing line means the printers developed by 3D Ceram, the materials. So the materials that we use, it is a mix of ceramic powder and photosensitive binders, also developed by 3D Ceram, and the post-process equipments if necessary, but also some services in order to help and assist our users. So at 3D Ceram, we like to say that additive manufacturing process for technical ceramic is that we can call a disruptive and complementary technology. Thanks to the benefits of additive manufacturing, it is possible to decrease the development time, and so at the end, the time to market. Also, as you might know, you can produce and shape some new design that you cannot do with any other processes. And as you just need the CAD file of the part, you can do some on-demand printing as you do not need any tools or any molds. One of the main advantages for additive manufacturing for all the materials, plastic, metals, and ceramic, of course, it is a fact that you only need the CAD file of the parts. But on the other hand, as I will show you after, it is still a process with post-process step and a low output capacity compared to some traditional process such as injection. This is why it is that I can call an inspiring technology. So before to explain you the process, I want to do a quick focus about that we can call the ceramic AM benefits and the design to function. That I can call a design to function. I will explain you for the ceramic part, but I'm convinced that it is the same for all the materials. You know, if you want to do the same parts that you are doing right now, don't think about 3D printing. It will bring nothing. You will not reduce the cost. If you are comparing A to A or B to B, forget. You really need to change something. So there are 3 ways to go. Either you start with ISO design. You change nothing, and you hope by saving molds, tools, you can reduce the cost. That's that we can call the ISO design. Or, second option, you create new design with new functions inside, which are difficult to make. You know, it does not mean it is a complex shape. It means it is a new design that you are not able to do with current technologies. Or we have that we can call disruptive design, when we integrate even more functions and we optimize the concept. You may have, for example, different parts in only one part. On this slide and on this picture, you can see an example of traditional parts and what we end up at the end. So for this example, we decrease the weight, and we have a better mechanical resistance of the structure. So, in my opinion, you know, this point is very important. Now, thanks to 3D printing and additive manufacturing processes, we have to design the part according to the function of the part, not according to the process that we have in-house. Few words about the market and forecast for 3D printing of technical ceramics. According to this market survey, the market forecast by 2028 for ceramic printed parts will be between, let's say, 56 and $1,300 million. So why there are such big difference? Because it depends a lot on the market which are using right now, if they are able to create products promising or not. Plus, it really depends if the big player will adopt to the technology or not. I can tell you, they are all investing, but they don't say a word. So we have NDA with everybody. They are all developing projects with 3D printing and qualifying the products in order to be the first on the market. So I do believe it is closer to $1 billion than closer to $56 billion. Another promising point, is the diversity of the market. Quite all the markets could be medical, space, energy, automobile, aeronautic, chemistry, and so on, invest in the process. Just before to explain you more specifically the SLA process developed by 3D Ceram, I just want to say a few words about the different processes to 3D print technical ceramic. Those processes can be classified in 5 major families according to the type of method. So you can find binder jetting process, selective laser sintering, called SLS, material jetting, material extrusion, and stereolithography, SLA. You know, in fact, there are no almighty process. Each process has its own advantages and disadvantages. So the most important to be considered when it comes the time to choose the right 3D printing technology is the kind of part that the users want to print. I will explain you on the next slide the interest and the advantages of 3D Ceram process. Okay, so few words regarding the SLA process that we developed. The stereolithography process developed by 3D Ceram use the photopolymerizations of materials thanks to a UV laser, so very low power, based on the top of the printer. As I explained you previously, the material that we use is a mix of ceramic powder and photosensitive binder. and each layer will be cured by the UV laser. So the first step is to do the CAD file of the part. Nothing special. Then the software printer will slice the part in order to indicate to the laser which area to cure at each layer. Then the printer will print the parts layer by layer to the bottom to the top. In fact, a blade will thread a thin layer of paste on the printing platform, and the UV laser based on the top on the printer will polymerize the area to polymerize. Then the printing platform will go down to layer thickness. The blade will thread another layer of paste, lasering, and so on and so forth, in order to print, to shape all the parts layer by layer to the bottom to the top. So after printing, the part is made with a mix of ceramic powder and polymerized binder. This is why we have to do two thermal treatments. First one, debinding, in order to remove, to burn the binder, and then sintering in order to close the porosity and to densify the ceramic. It is during the sintering process that we have some shrinkage, including between 10 and 20%. And the shrinkage only depends on the chemistry of the formulation. So the SLA process developed by 3D Serum uses UV laser on the top of the printer. And as I told you, we print the parts to the bottom to the top, as you can see on the video. You know, the combination of top-down process and UV laser on the top allow to obtain fully dense parts with very thin details if necessary, but also low shrinkage during the sintering step. So one of the main advantages also of the SLA process developed by 3D Serum is the lack of links between the parts and the support. With quite all the processes for metal, plastic, but also other processes to print technical ceramics, you need links, pillars between the parts and the support, who require a lot of manual job during the post-process, but also a lot of risk for the ceramic parts. And thanks to the top-down process and the viscosity of the slurry, we do not need any links between the part and the support, as you can see on the picture and on the video. So that you can see on the picture and the video, sorry. For example, if we want to print the white part, so we design the support in red, and during the printing run, we had a very small gap of uncured slurry between the part and the support. So we don't have any link, any pillars. This is why after printing, it is very easy to remove the support and just take care of the part. You know, to make easy and user-friendly the post-process is one of the key points for the adoption of the process by the key players and the industrial groups. Now, I want to show you a short video of the process. So as I told you, the first step is to do the design of the part and the support with any design software. Could be SolidWorks, CATIA, NX, and so on. Then we send the STL file to the printer software, and the printer software will automatically slice the parts. Slice means indicate to the laser which area to polymerize at each layer. Then just have a look into the printer. So you have a tank for the paste, okay, the mix of ceramic powder and photopolymerized binder. The printing platform is in the middle of the printer. The recoater with the blade in order to spread the paste on the printing platform, and the UV laser, so very low power, based on the top of the printer. So I will explain you later, but we can have different size of printing platform with this printer. You can see the high viscosity of the slurry. And at the beginning of the printing run, so the blade spread a thin layer of slurry on the printing platform, and the UV laser, very accurate, will cure the area to cure, as you can see on the video. So after all the curing of all the layer, we remove the printing platform to the printer, and we have to do that we call the cleaning step. So we have to blow in order to remove the uncured slurry in contact to the parts. So we blow with a mix of compressed air and a specific solvent in order to, yes, to remove the uncured slurry in contact to the part. And as you can see, it is very easy to remove the support to the part. We do not have to cut any links, any pillars, and so on. And after printing, first thermal treatment, debinding in order to burn, to remove the binder, and then sintering in order to close the porosity and to densify the part. And then after, of course, control of the size of the part if you need, if you want. So, few words regarding the mix that we use in order to print parts, called 3D mix. We developed some standard mixes. We can also develop some on-demand mixes with a specific powder. And keep in mind that our users can develop their own mixes and own printing parameters as all the printers are open. It is open printers, open software, so our customers, our users are able to develop their own printing parameter if they want to do it. About the standard mixes available for our users, we developed some oxide, such as alumina, zirconia, cordierite, alumina, toughnet, zirconia, HAP, hydroxyapatite, and TCP, tricalcium phosphate for biomedical implants, but also some silica-based material for the foundry cores. We develop also nitride, such as silicon nitride and aluminum nitride, and soon we will offer silicon carbide. Just for your information, nitride are mainly used for aerospace due to their excellent thermal properties. HAP and TCP are only used for biomedical implants. I will show you after some examples. And oxide, such as zirconia, alumina, and silica-based, are used for the industrial needs. So 3D CRM provide 3 different printers in order to meet all the needs, from the lab to the mass production. First, the bigger printer, the CERAMaker 3600, with a printing platform of 600 per 600 per 300 mm. Then, middle size, the CERAMaker 900 Flex, with a printing platform of 300 per 300 per 100 mm. And the smaller one, the CERAMaker 100 Easy, with a printing platform of 100 per 100 per 150 mm, dedicated to laboratories, universities, and research centers. And you know, the most important point is the fact that all the printers use exactly the same process, which is a key point for the adoption of technical ceramics additive manufacturing process. Because you know, a user, a customer can develop some new possibility, new process with the small printer, and then they can do a quick and easy scale up on the big printer. You know, if you develop some amazing things at a small scale, and if you cannot do a scale up for the industrial needs, unfortunately, it will bring nothing. So for all, not only for ceramics, but also for plastic and metal, it is very important to have the possibility to do a scale up, to develop some new things at a small scale, and when it is ready for the industrial needs, to be able to use a bigger printer with the same process. It is clearly a key point for the future of ceramics AM, but also AM for all the materials. I just want to say few quick words about each printer. So as I told you, the bigger one is the CERAMaker 3600 Ultimate with a printing platform of 600 per 600 per 300 mm. Of course, this printer is dedicated to the mass production and the production of big ceramic parts. That's the last printer, the last machine developed at 3D CERAM. You know, with this big printer, we are talking about mass production. Our objective is not to compete with injection molding, which is very useful for the mass production. But you have to keep in mind that additive manufacturing is a way to open new markets, new geometries. Engineers can think differently how to print the parts, how to add some functions, how to group several parts together to make only one part. And thanks to our 20 years of know-how for printing parts, because if you remember at the beginning, I told you that at 3D Ceram, we start by printing ceramic parts in 2001. Thanks to our know-how, we can advise and assist our user with ROI, which means return on investment, which is clearly a key indicator tool for investment. Then just few words about the C100 Easy with a printing platform of 100 millimeters square per 150 mm. So of course, this printer is developed for laboratories, universities, and also research center. The objective is really to play with. It is that we can call a user-friendly printer, and the users can launch a production in 20 minutes. Customers can develop new parts and develop with prototype. But on the other hand, it is also possible to use this small printer as a printer for small series, as you can see on the slide, with a lot of small parts on the same printing platform. And to finish with our range of printer, our that we can call historical printer that we developed in 2005, the C900 Flex with 3 different sizes of printing platform. So with the same printer, it is possible to use 300 per 300 mm, but also 300 per 200 and 300 per 100 mm. So this possibility to use a different size of printing platform with the same printer is very useful because you just have to take care of the size of the part and the number of parts that you want to print, and you can adapt the size of the printing platform. So just to compile, and as I explained you, 3D Ceram provide that we can call a large range of printer, from lab to the mass production, small, medium, and big size. But one time again, and I really want to insist on this point, all the printers use the same process, which is clearly a key point for us. So, is this process ready for the mass production? I will try to give you some answer today. You know, actually, we have to keep in mind how technical ceramics additive manufacturing can meet the industrial requirements to be used at a large scale. First point is to be able to provide a printer in order to print a lot of parts and big parts. Second point is to provide a range of printers with the same process to allow a quick and easy scale-up. So it is exactly that I explained you on the previous slide. Then, you know, it is very interesting because, you know, the COVID-19 pandemic has forced some companies to question many things and has revealed how volatile supply chains can be. Because many companies cannot reach out to their suppliers, or the suppliers cannot produce parts due to lockdown, for example. And thanks to the benefits of digital production and the possibility to stabilize the supply chain, technical ceramics AM and SLA is now a real answer. I will show you some examples. This first example concerns a cryogenic optical support for a mirror at 80 Kelvin, so cryogenic temperature. For these applications, we need to reduce the weight in order to reduce the thermal mass of the part, but keep also outer surface of the allowable volume. Also, to have as low roughness as possible. You can see on the picture below the first design that we received. This design was made for metal milling. So after redesigning of the part for ceramic AM specification, we print it with alumina, we sinter it, and the customer, at the end, did the brazing of the metal insert, the titanium insert. This is a first example of concrete application. I want also to share with you this case of parts print with silicon nitride, SA3 and 4. As you might know, silicon nitride is one of the ceramics the most used for the space application due to the thermal and mechanical properties. But first, you know, it is not so easy to print silicon nitride. And it is also complex to obtain good quality after sintering. And good quality means quality conform to the space applications. This prototype, this design that you can see on the slide, was designed by the French famous company Thales Alenia Space to represent critical shape for the space application. The global part is a hub, and we isolated and we designed part of this hub to print it. So you can see on the slide some picture of the parts after printing and sintering. But as I told you, to print silicon nitride is only a first step. To obtain a good quality of silicon nitride after printing and sintering is the final objective. So this is why, still in collaboration with Thales Alenia Space, we print some beams in order to check the mechanical properties. So after printing, sintering, and 4-point bending tanks, we obtain very high density. As you can see on the graph, superior to 97%, and 4-point bending strengths have shown a very good strength results. As you can see on the graph, we obtain a tensile strength of approx 800 MPa, megapascal, and a Weibull modulus of 11.5. These results are very good, very, very good, and it meets the specification for space, as they are similar to silicon nitride made by traditional process. I just want to insist on the point that in this case, we are speaking of pure silicon nitride, beta silicon nitride. It is not a derivative of lower purity. You know, it is crucial for all of us to demonstrate that 3D printed ceramics can obtain the same property than ceramic made with traditional process. It is clearly a key point for the adoption of the process. Then, just a few words about the microstructure of the parts, who confirm that I explained you just a few slides ago. The pictures taken after sintering shown an homogeneous microstructure and no pore cluster. As you can see also, the shape of the silicon nitride grains is typically hexagonal, which is good and typical for beta silicon nitride. Then I want to share with you one of our last application, antenna for nano satellites. During this year, we successfully achieved a big project with one of our users who produce antenna for nano satellites. Nano satellites are made for low Earth orbit at approx 400-600 km to the Earth, mainly for telecommunications. And the antenna are made specifically for telecommunications. You know, the first point, very interesting, is the fact that they need ceramic and they need zirconia due to the excellent permittivity of this ceramic. And then they need 3D printing and they specifically need SLA to produce lattice design, parts with low roughness, thin details, accuracy, and also repeatability. For your information, the lattice design increases the property of the antenna and of the ceramic parts also. The first zirconia part into a nano satellite will be in the space in few weeks. And as you might know, with the nano satellite constellation, the future is very bright for this application. So as I told you on the previous slide, the ceramic parts print with SLA process can be used for satellites, for new space. That we can call a new space use small satellites. So they need small ceramic parts as the thermal management is much more complex and tricky for them in order to obtain the final performance. This is why a large range of ceramic can be used, such as alumina, zirconia, silicon nitride, or also aluminum nitride, and the applications also are broad. It could be used for thruster, for heat insulator, or also optical parts. You have to keep in mind that optical application is one of the bigger market for new space, but also structural application, where you use the properties of technical ceramics, such as silicon nitride or alumina, and you can really have a structure which will not be deformed with the difference of temperature in the space. So, to explain, when the structure sees the sun, it may go up to several degrees. And when it does not see the sun, it may go up to, let's say, minus 40, 50 degrees. And when, with this difference, with this gap of temperature, the structure is deforming and the satellite is not working well. And it is not the case with the ceramic parts. Another application very promising for technical ceramic AM that I want to share with you is a foundry course for investment casting. You have to keep in mind that foundry cores are an essential part of the production of blades for the combustion engines. The blades are used to cool down the engine while in use, to facilitate the workings of the motor, to lower the fuel consumption, and to decrease the engine emissions. This is why the need for complex core design has increased dramatically with customer demand for smaller, more efficient, and cost-effective engines. Another point very interesting, and as you can see on the slide, currently, in order to produce foundry cores, users have to produce and assemble a lot of small injected parts. So it is long, it is complex, and it generates a lot of waste. And thanks to 3D printing and a SLA process, they can produce the same design in one pieces, an even more complex and efficient design. Foundry cores are made of porous ceramic. It could be alumina or silica based. It is made of porous ceramics because users need to remove the ceramic parts after the metal casting. This is why the quality and the properties of parts are very complex to achieve because it combines refractory properties, low shrinkage during casting of metal, but also mechanical properties. On the picture, you can see the first part cast into metal without any defect. You can see a CT scan, and the CT scan made on the part confirms that there are no defects after the casting of liquid metal on the ceramic part. Now, I want to share with you another possible application for technical ceramic 3D printing. I want to do a quick focus on medical implants and specifically skull implants. First, our process is mainly used for skull implants and cages for between vertebrae. User can also print ace implants, as you can see on the slide. Ceramic used for this kind of parts, for implants, are mainly hydroxyapatite, HEP, and tricalcium phosphate, TCP, because the chemical composition of these ceramics are very close to the bone, to the real bone. First, I want to explain you more in details the skull implants. The use of 3D printing for skull implants is obvious because, of course, nobody has the same defects. But it is not the only reason. Thanks to 3D printing and SLA process, you can have several functions in one part. For example, on the skull implants that you can see on the slide, you have 3 different functions. First, we have a porous area on the 2 centimeter close to the border. This porous area will allow the osteo-integration of the part after the operation. Then we have a dense area in the middle for the mechanical property and the stability of the part. And then, as you can see, we have some big hole all around the part. The aim of the hole is to allow the surgeon to fix the implant to the skull with bioresorbable wire. So on the same part, as I explained you, we have 3 different functions, and only SLA and 3D printing can allow that. Few words about the process to print and produce such part, a skull implant. First, number 1, the user receives the scanner from hospital. Then, step 2 and 3, the user have to redesign the skull in order to design the implant. Then, the printer software will slide the part, as I explained you at the beginning, and after printing, we have to clean, to debind, and to sinter the part. Then, of course, it is a step number 10 and also 9. After sintering, the user has to check the geometry of the part and to sterilize, of course, the implant for the operation. Okay, so I'm sorry for the picture, but I think it is very important to show you that it is not only slide. It is not only my words. It is reality today to use ceramic additive manufacturing for implants for real human patients. So you can see on the slide a case for orbitofrontal implants. So as I explained you, the hospital sent us the scanner of the patient. We design the part. We print the part with HAP. You can see picture during the operation, and you can see the scanner 1 year after. And it is very important. You can check that there are no gap, no hole between the skull and the implants, because the osteo-integration of the part was excellent, as the chemical composition of HAP is very close to the bone. Another case, very interesting, because the lack of skull, as you can see, was very important. It was, if I remember well, 5 years ago. And as you can see on the slide, we print the implants with 3 small parts, the blue one, the red one, and the yellow one, because the surgeon was more comfortable with 3 small parts than 1 big part. More and more hospitals and surgeons also prefer ceramic implants with biocompatible ceramic due to some disadvantages of the titanium implant. With titanium and metal skull implants, you can have another risk of trauma during another violent impact due to the transmission of force and deformation of the metal plate. Also, with titanium implant, you can have a risk of releasing of metal ions on the cells close to the implants, but also a risk of cutaneous erosion, for sure a bad aesthetic result, and of course, a lot of radiological artifacts. But the most important point is the fact that with metal implants and with titanium implants, there are a risk of infection after the operation, up to 22%. On top of skull implants, cages and ACE, user can also print sinus floor, also encapsulation boxes for electronics, for example, for pacemaker. Of course, more and more of our users use 3D printing to print dental parts with zirconia, but also some non-implantable parts, such as surgical tools with alumina and or zirconia. Now, I want to speak with you about the hybrid process. The hybrid process is a new process in order to print a ceramic and up to 3 other materials on the same time. The other materials could be another ceramic, plastic, metal, or something else if you have another ideas. So you can see on the slide that we had 3 nozzles on the printers in order to print the other materials. First, so of course, I will show you some videos in order to explain you how does it work, but I just want to start with some generalities about this hybrid printer. We made the choice to develop it with the same process. So we use the same process and the same printer with SLA process for the main ceramic, with UV laser on the top, and we had 3 nozzles, 3 specific nozzles in order to print, in order to deposit the other materials. Before any deposit, we blow the uncut paste in order to remove it and to create a gap. Of course, I will show you some video on the next slide. But the most important point about the hybrid printing, about that we can also call multi-material printing. You have to keep in mind that printing is just one step. After, you have to do debinding and sintering. And during the sintering step, you will have some shrinkage. So if you print a hybrid part, all the components inside must have quite the same shrinkage in order to avoid any cracks, any decohesion during the sintering step. So one of the first questions is why hybrid process with technical ceramics could be used for some applications. First case on the right side, it could be used for multi-material and metallic material for LTCC, HTCC, and embedded electronic function. You know, the process to shape and to produce LTCC and HTCC are well known, but it could be easier and cheaper with additive manufacturing process. Another case in the middle for lattice structure. If you combine on the same part ceramic and plastic, plastic will be burned during the debinding step, and it can allow you to shape some new structure that you cannot shape with any other process. And last case, in the left side, if you combine again ceramic and plastic, you can shape very complex internal canals. Because if you print plastic into the canals, you do not need to clean the part. You just need to put the part into the debinding furnace after the printing step, and the plastic will be burned. So, as I explained you, the aim of the hybrid process, the multi-material process, is to deposit plastic, metal, or something else on the ceramic substrate. So just before to show you some videos, I want to explain you the flow chart. You have to keep in mind that the hybrid process is again a layer by layer process. We print a hybrid part layer after layer. So the flow chart is this one. First, we scrap the ceramic paste on the printing platform. So it is the same things than for the standard process. Then we cure the ceramic paste only on the area where we need fully dense ceramic at the end. So it is again made the same things. We scrap and we cure the ceramic paste. Then we blow the uncured paste with a specific nozzle in order to create a gap, to create a groove on the area where we want to deposit another material. So we blow with compressed air. After blowing a specific nozzle that we can also call a dispensing system will come in order to deposit the other materials into the gap, into the space. And then to finish, the UV laser will cure the other material in order to have something stiff, something stronger. And then do it again, scrapping, curing, blowing, printing, and curing. I will show you some video. I think it will be more clear. So on the top, you can see, as I explain you, it is the same printer, okay? And we had a specific scrapper on the top with 3 nozzles in order to deposit up to 3 other materials. Then, second video, as I explain you, after the scrapping and the curing of the ceramic paste, a specific nozzle will come in order to blow compressed air. So it is exactly that you can see on this slide. The specific nozzle blow compressed air, only compressed air at low pressure in order to remove the uncured slurry on the area where we want to deposit another things. So we blow compressed air in order to create a gap, a groove. And then when all the gaps are created, a specific nozzle will come in order to very accurately fill each gap. So I'm sorry, on this video, it is not easy to see because we fill the gap with plastic. So it is transparent. But I can tell you, this nozzle fill each gap, each groove with plastic. So this, it is some videos, okay, in order to illustrate the hybrid process in order to print multi-material parts. Then I really want to share with you our vision for the coming years, because I think it is important for all of us. You know, the next development that we are presenting to our customers, it's automatic line. Right now, as I explained you, we print, we clean, we debind, and we sinter the parts. And what we promote is automatic line, where the customer just have to lead the paste into the printer, and then everything will be done automatically with loading printer, cleaning device, and the kilns. So we are developing this automatic printing line, in order, of course, to decrease the waste of time between each step of the process, but also increase the profitability of the process. So I want to add a few words to conclude our discussion. You know, while the current situation is very bad for the world economy, I see some companies, some big players, now realizing the potential of additive manufacturing, because people start to think differently, and they are now considering digital production technology as the real means to overcome these issues. This is why technical ceramic AM market is an expanding market with a growing demand for industrial printers. And industrial printers means the possibility to print big parts or a lot of parts, but also to print ceramic with good quality. This is why I do believe, and I am convinced, that the time to use additive manufacturing for mass production is coming, and it is really the time to produce now. You know, the applications already on the market and qualified that I showed you is a real signal. Just before to finish, do not hesitate to follow us if you want to learn more about 3D CRM and technical ceramic printing. We have a LinkedIn page, and we publish some news each day or every two days. Also, we have a YouTube page, and we publish some videos each week. We launch since few weeks a series called 3D CRM Inside in order to quickly answer to the most common question that people can have about technical ceramics 3D printing. And also, as I cannot travel to Philippines in order to see you, as you cannot travel to France in order to see the printer due to the current sanitary situation, we launch since few days that we can call a virtual showroom. So if you want to have a virtual look on our company, our printers, and our parts, do not hesitate to have a look on our virtual showroom. So thank you again. Thanks again to all the organizations. And of course, if you have any question, do not hesitate to ask me or to contact me. Thank you again. We have to develop a kind of metal ink in order to be able to print metal ink, with the nozzle, but it is clearly possible, and we already did it to print metal and ceramic parts. But in this case, as I told you, we have to develop a specific metal ink in order to be able to use the specific nozzle.
Thank you. Laureen, does that answer your question? Dioki is asking, is it possible to make transparent objects for optics, such as lenses?
So at this time, no. At this time, we don't have formulations to print transparent parts, but we work on some project with some specific powder in order to be able to print and to shape transparent parts. But clearly, at this time, it is not yet ready.
Thank you, Doki. Laureen has a follow-up question on metal printing. What is the highest resolution or smallest dimension that can be printed?
Okay, it is a very good question. So, as I explained you, and as it was explained on the short video that I showed you at the beginning, the size of the laser that we use is 30 micron, 30. But we cannot print a smaller pixel of 30 micron. When so you have to keep in mind that the paste that we print is a mix of ceramic powder and photosensitive binder. So when the UV light cures the paste, we have that we can call scattering, which means that the smaller pixel that we can print is bigger than the laser size. So the smaller pixel that we can print is 100 micron, even if the laser spot size is only 30.
Okay, thank you, Maxence. Is the print, KG is asking, is the printer open source? Have there been explorations on copper-infused ceramics? Thank you.
So, the printer is open. Okay, I think we have to explain the difference between open and open source. 3D ceramic printers are open, which means that any customers, users can develop and create his own printing parameters. Open source for me means that users can have a look on the 3D serum parameters, and it is not the case. With our printers, users can use 3D serum parameters to print alumina, zirconia, and so on. They can also create their own preset, but they cannot have a look and they cannot know how are made the 3D serum process, because it is our know-how. So it is not open source, it is open.
Mhm.
And about the second question, there been any exploration on the copper? No. So first, I think it is very important for me to explain what is doing 3D serum. 3D serum is that we can call now a process provider. So we provide the printers, we provide the parts, and we print some ceramic parts every day in order to show to the users that the process is okay for their specific application. But 3D serum, we don't have the number of people and the time to develop a lot of new things. So it is the job of our customers, of our users, to develop new things. For example, we already sold 5 or 6 hybrid printers all around the world, and it is the user job and the user know-how to develop new slurry for copper, for silver, for tungsten, and so on, in order to use a hybrid printer. We cannot, at 3D serum, we cannot develop all the things, because which is amazing with the hybrid process, it is a fact that you can do a lot of things. Quite all that you want. You can print a ceramic with copper, silver, tungsten, gold, and so on. And of course, we cannot develop all the slurries. So yes, I just want to explain that it is not the 3D serum know-how, it is not the 3D serum job activities to develop all the slurries. It is also our users' know-how to do it.
Thank you, Max. Vladimir is asking if there are any safety certifications to use the ceramic materials you mentioned in medical use.
Yes, so it is a very good and a very important question. Of course, users and 3D serum need certifications to print and to produce skin implants or any kind of implants. So 2 things. First, it is a 3D serum certification to provide a paste with a good ceramic powder for implants. So it is our job and our certification to provide to all of our users all around the world to provide a paste with certificate powder inside. But after, it is a customer job and the customer certification to do his own certification in his own country. I will give you a very easy example. I am in French, you are in Philippines. I have some other customers in Germany, in China, and the certifications are not the same for all the country. It is not the same in French. I'm sure it is not the same in Philippines. It is not the same in China. So the laws are different for each country. This is why it is a customer and the user duty to do his own certifications according to the laws of the country.
Thank you, Maxime. Are there any other questions from the chat group? Okay, I posted the links to the 3D Serum LinkedIn page, as well as the website with the virtual tour.
Yes.
Yes, you can go visit. You can reach out to Maxence if you have any further questions. The local company partner is OmniFab, correct?
Maxence?
Yes. OmniFab.
Yes.
So
Exactly.
OmniFab is the local partner. If there are no other questions, we would like to thank Maxence for being a part of FabFest 4. Thank you so much.
Thank you.
You can visit next time when things are better.
Me too. Yes.
Come visit. And we would like to thank BTI and DOST and AMSEN for organizing FabFest. Maxence, do you have any other things to say before we end the session?
No, for me, it's okay. I just want to say thank you to all of you to be there today. I hope it was interesting for you to learn more about technical ceramics 3D printing. And if you have any question, do not hesitate to ask me, to send me email, or to call me. I will be more than happy to answer you. And I hope to be able to come soon in Philippines in order to meet you.
All right. Thank you, Maxence, for sharing your knowledge. Amazing talk. Thank you,
Thank you.
everyone, for coming and joining the Zoom meeting and conference. And I think that'll end our session for now. Take care, everyone.
Okay, goodbye.
Bye-bye.